All right, now look at this, guys. All this time, and I realized that I made some mistake here, and let's see about fixing it. Because in fact, it's not cosine of alpha that we want to get the x component, because I was thinking, I've been wrestling with putting a negative sign there, but that was because I was thinking about, okay, if I use cosine of alpha, then I'm talking about a vector that's in the quadrant 2, so I'll just hit it with a negative sign. But we have to be a little careful about that, because we'd have to monkey around with signs and limits, and so let's be careful here, and let's first of all, let's get rid of this for now, and let's see if we can work this out. So it's really cosine of beta. And so now we have to, but we want this in terms of alpha. So we see that beta is equal to alpha plus 180. And the thing is, I've worked it through by just hitting that with a negative sign. Excuse me, and it didn't work out to my satisfaction, and I can't think of something better. And so let's, so that becomes cosine of alpha plus 180. And basically is saying negative cosine. And because if I hit anything of 180, that's going to get me the negative value. Okay. So, well, I may end up having to delete this, but so let's then try it. E of x is going to equal to k lambda over a times the minus of cosine of alpha d alpha. And then I've got my limits of integration. And we determine 3 pi over 4, 5 pi over 4. And, okay, we can say that this is now 135 degrees, 90 plus 45. And then we added, the length is 90 here, so that makes this 225 degrees. So let's look at our DE. If I say 135 degrees and I plug it into cosine, I get a minus 0.7071. And that means that, but I know that DE is positive. So if I've hit it with the negative, fine. And let's see about what happens at 225. So 225, enter. And let's say cosine, and I get a negative number, which is fine. So let's do it one more time. 135 cosine is negative, fine. And then at 225, cosine's also negative. So if I hit it with the minus sign, I get DE in the right direction each time. Okay, so let's take a look. So if I integrate this, I get k lambda over a, and integral should be minus sine of alpha, and I'm integrating from 3 pi over 4. I didn't write it here. Or if we like, let's just use our angles right away. I'm going to integrate from 3 pi, 135 up to 225. So if I take the sine of 225, I do expect that to be a negative number. Sine, and it is. Oh, okay, so then I hit that with a negative sign. So let's write it out. K lambda over a minus sine of 225 minus sine of 135. Okay, so I get a minus 0.7071 for sine of 225. Hit it with the negative sign, and I get 0.7071. And now, let's see, clear it. Now I take 135, and I get the sign of it. I expect it to be a positive number up in quadrant 2, and it is. So I hit it with the negative sign. So I've got negative 0.7071 minus times a minus, and I end up with 1.41 times k lambda over a, and if you like, so this is the EX component, magnitude. So far so good. Somehow I thought the minus sign was wrong a minute ago, but all good. So now let's take a look at the y-axis, and first of all, let's double check. If I once again use my beta, which beta equals alpha plus 180, then we say, okay, if we're going from 135 to 225, then let's think about this. So at the start, 135, though it's going to be excuse me, clear. So 135, enter, and 180, and oh crap, let's see if it works. Yep, okay, 135, enter, 180 plus. So let's take a sign of that. So it's a negative number, and that's cool. That's what we want. If we use beta, same as before, because it's again, it really should be beta for the time being. And so let's think. Yeah, so if I did, so that's fine. That's negative. And then if alpha equals 225, and now we add 180 to that, and then we take the sign, that's positive, so that's cool. We would expect at this point the y component is going to be positive there, so that's all good. Now, what happens if we just use 135 then? So 135, and we take the sign, is positive, so that's no good. Okay, so we need to hit it with a negative there at 135. But what about a 225? So 225, enter, hit it with the sign. It's also, it's negative, but when I'm at 225, I want it to be positive. So it looks fine. We need to then say, and you could look it up in a table too, right? So sine of alpha plus 180 equals negative sine of alpha, just like before with cosine. So then that means that, just as before, we're going to say that E of y equals k lambda over a times the negative sine of alpha d alpha. And then our limits, well, we'll just get pretty tight in there just again. So that means if we integrate sine, we get negative cos, but we have a negative sign, so we end up with cosine of alpha from 135 to 225. And so that's going to be k lambda over alpha a times cosine of 225 minus cosine of 135. And let's see what we get. .225 cos is a minus 0.701, and you go here, and cosine of 135 is also a minus 0.7071. But now when we hit the sign there, we see it's equal to 0. So it's kind of unsurprising that EY equals to 0, and the resultant E field is along the x-axis. Now, keep in mind that we could have given you, say, some kind of piece of charge, right? So different limits of integration. So at that point, you might expect a final result like this. Okay. Now, this is a pretty simplified problem, but the point is that we want to enunciate the steps involved in any problem like this And so give me a minute. I gotta get my snipping tool over here. Isn't that cool looking? And there we go. Let's get it all. And this, I'm just lifting it. It's just easier to do this from a PDF I made. And so let's go through it. A good diagram. Define a DQ somehow, because the idea is, overall, remember, is that we want to use the E of a point charge, because we want to exploit the fact that when we integrate the integral, like the dx, the d alpha, the dq, is a limit as this would go to 0. And the limit that dq goes to 0, it does become a point charge, no doubt. Keep in mind now you're defining a dE when you do that, not E yet. So define your dq in the coordinates that you have, and remember that meant for us that dq equals some charge per unit length, times the angular width, but then we had to hit it with the radius, in this case, a lambda d alpha. Then you need to define r in the coordinates that you have available to you. And here we got lucky because r was constant a if I used this coordinate system of the angle alpha. Now notice that I put alpha here inside here, and that's wrong. Although I suppose if we could have, it would, but we want to always be careful, and alpha is defined from the 0 point. Okay? And then the variables of integration, components, you might have to use components. I added this late, I added that in later in this case. And so once you've defined dq, you may have to go back, because if you can't, and when you may have to, then you go to the variables of integration, and you may say, oh crap, I have to redefine dq because I have to fit it in. So there's some sort of back and forth on that. Then you have your limits, and then as we did, we just double checked our diagram, the way we defined the angles, and then we want to define the components and such. So yeah, you have to go back and double check. And then just to show you something that I meant, wrong button, hold on. If I go back to, so let's show you a different situation. Delete this. And now I have the snipping tool once again. And let's snip this. And so, and we'll paste it. I suppose I can crop that a little bit. All right, so you see here that if I pick this point, this alpha, for example, is not a good variable of integration. And so if we have a dq here, it's going to have to be a much different, let's see, where are they, shapes, right? It's going to be a much different definition of R for the dE equals dQ and K over r squared. So we'd have to come up with some different variable of integration. And because, I mean, we could try out, that wouldn't work. So probably we'd have to do an integral in x and an integral in y. But, you know, that's pretty darn complicated, and it's not, one wouldn't expect that you would be expected to do that in Physics 2200. All right, there we go. Oh, this one went 20 minutes, but now we have a full set of videos.